In this video, we are going to talk about k-factors and some other decompositions of complete graph. So first off, a k-factor of a graph is a k-regular spanning subgraph of G. All right, so you need to go back and remember what a k-regular subgraph is. A k-regular subgraph is or k-regular graph is a graph where each vertex has exactly the same degree. Okay. So for instance, here we have the complete graph on 6 vertices. It is 5 regular, right? Because every vertex has degree 5. 1, 2, 3, 4, 5, 1, 2, 3, 4, 5, and so on and so forth. So 5 regular. All right, and so a k-factor is k-regular, and then it also has to be a spanning subgraph of G. So remember, that is a subgraph of G that contains all of the vertices of G. Okay, so that's what a k-factor is, and in particular, right, one of the things of interest and the thing that we'll use in the next theorem is related to the proper edge colorings that we had for the complete graphs in the previous section. All right, so what you're looking at here is a proper edge coloring of the complete graph on 6 vertices. So you can see, right, every vertex here, all we would need to do is just to check and see, okay, is there one of each color? Since we're talking about the complete graph, right, that's what we would need, one of each color here, and sure enough, there are. Okay. All right, so if you take the subgraph, let's say, consisting of the yellow edges, okay, only. So if you look, that is going to be a spanning subgraph because you can see here that A1, A3, A2, A4, A5, A4, A0, all of those are in the graph. So that makes the set of yellow edges along with the endpoints of those edges makes that a spanning subgraph of G. And in addition to that, it is also one regular. Okay, you can see right here that every vertex on that graph that we're talking about, the yellow edges and the included vertices, every one has degree 1, right? If you're just looking at that subgraph. All right, so that is a one factor of this graph. Not only that, all of the colors, right, the edges, the subgraphs of the all that are of all edges of one color and the endpoints included are also one factors, okay, in here. So here, if you look at the blue graphs, right, just the blue edges alone, don't look at any of the other edges, you can see the endpoints here are A3 and A4, here A2 and A0, A1 and A5. So that means, right, that it is all of the blue edges and the endpoints form a spanning subgraph of G, and it's one regular. Every the degree in the subgraph, right, is 1. Okay, so all of those are one factors in here. All right, so what we have here really is a decomposition, right, into these one factors, and that is induced by that proper edge coloring that we talked about in the previous section. Okay. All right, so we already talked about the situation for k sub 2 n plus 1. For k 2 sub n, right, and this is theorem 2.3.2 in our book, it has a decomposition into n minus 1 Hamilton cycles and a one factor. Okay, and so we're just going to kind of illustrate how that comes about. And this is not, actually, this is just the same picture in the previous slide. This doesn't show the decomposition, so this is still the proper edge coloring. But that's where we would start when we're talking about this. we would get that proper edge coloring that's guaranteed from section 2.2. That is in Theorem 2.2.3. So we start off with the proper edge coloring. And then all we do is take the edges that are colored one color together with all of the edges of another color and put them together. So that's what I'm going to do in this next slide here. So in this slide, I'm going to take the red ones and switch them over to blue. So basically put those together. So this is no longer a proper edge coloring now, but that doesn't really matter. We're just after the decomposition. If you look, the edges that are blue along with its endpoints form a Hamilton cycle. So if I start here at A0, then I go to A1, A5, A3, A4, A2, A0, A1 like that. So that's a Hamilton cycle. Okay. All right, and then I'm going to pick two more colors and kind of merge them together exactly the way I did before here. So next up, I picked the green and the yellow edges, and I'm going to change all the yellows to green. That's going to give me another Hamilton cycle. Okay. And just checking the green one. If I start at A0, right, I go to A3, A1, A2, A5, A4, back to A0. So we have a cycle and it's a Hamilton cycle. And that's it. We can't really do any more of that. So what we have here are those two Hamilton cycles, the blue edges and their endpoints, and another Hamilton cycle, the green edges and their endpoints, and together with this one factor here that are the black edges and its endpoints. So you can see that's a decomposition of this complete graph. Okay, and the same thing happens for any even complete graph of even order. It will have this decomposition into Hamilton cycles and a one factor. So for the odd ones, right, we have a decomposition to n Hamilton cycles for the odd ordered complete graphs. For the even order, we have a decomposition into n-1 Hamilton cycles and a one factor. All right, and that is it on this one. I'm just going to talk about the idea here and then move along.